Hello again. Let's continue our discussion on this Hardy-Weinberg equilibrium. And again, it's going to give us a way to provide a metric to measure what's happening in a population. So Hardy and Weinberg were, one was a mathematician and one was a biologist, and they kind of collaborated together on this mathematical equation. Now, like I said, we're not going to worry too much about the deep math, but I want to at least show you what they proposed. So remember, a population is not evolving, it's in equilibrium if those numbers stay the same. Now, what Hardy and Weinberg what they did, now this is not a full list, but it's pretty much the standard list you see in most biology texts. Hardy and Weinberg proposed that there were 5 conditions that need to be met for a population to not be evolving. There should be no natural selection. In other words, all animals or plants have an equal chance of surviving and reproducing. There are no mutations happening. There is random mating. In other words, all animals and all plants in the population have an equal chance of passing down their genes. There's nobody leaving and nobody coming in, because if that happens, then you're going to change the frequencies. And then a larger population will change less. So again, this is why we worry about endangered species. The smaller a population is, the more likely it is that we're going to see changes that may not be recoverable. So these are the 5 conditions for equilibrium. So what happens when these are not in equal? What happens when these things happen? So let's take a look at that. A population would be called evolving or is not in equilibrium if the allele frequencies are changing. The population I need to change that. The allele frequencies change. The population would then be considered evolving. So let's take a look at these. There is natural selection. There are mutations. There is not random mating. In other words, some animals are going to attract mates or reproduce more. There are some animals or plants leaving or coming in, and we'll talk about how plants can do that, but that's the 4th condition, or the population gets smaller. So again, if any of these 5 things happen, that's going to change the frequency. So let's take a look at natural selection. That was the first one. So in artificial selection, what ends up happening is that breeders choose animals and plants based on the genetic traits and only breed those with traits they want. Probably some of the best examples of this would be dogs, corn. Believe it or not, the corn that you eat in the summer for corn on the cob at a cookout, good memory, would be different than the corn that you use for popcorn. And again, it's different from what farmers use to feed their poultry or cows or other animals. So we have selected for different corn traits. Chickens, the chickens that you see that are laying eggs are going to be different from the chickens that we raise for meat. And of course, the dog breeds and the cat breeds that we like. So that is natural selection. Even scripture shows an example of artificial selection. I'm going to post an example of where this happened in the Old Testament. Now, natural selection simply just means that this happens in nature. Notice in artificial selection, we're going to choose the animals and plants based on the genetic traits. So we want corn that's going to pop better, and so we want to choose corn that has different amounts of starch versus sugar and water content, and that's going to cause them to pop more fluffy and better, and that's what we like. If we want a dog that has a spotted coat, we're only going to let those dogs breed, and thus we have the Dalmatian. If we, for instance, our Labrador retrievers that we looked at, Labrador retrievers by the breed standard only have solid coats. Now that doesn't mean that Labrador retrievers never have spotted coats. It just means the breeders will choose to only let those dogs with solid coats breed. And then we get a Labrador retriever that would have solid coats. Now, in natural selection, what we would see is that the traits that are better adapted to the environment allow organisms to either survive longer or reproduce more. So maybe there's an animal that is going to produce 6 eggs instead of only 2. Well, that might mean that they're passing on their traits to the next generation more frequently. Or maybe there's an animal that is attracting more mates. Well, that means they're going to reproduce more, and then they're going to pass down their traits. Now, if that's the case, then more of those alleles are in the next generation. We would say that that animal or plant has a selective advantage. Now, if that happens, then we would say that that animal or plant has a selective advantage, and that means that the alleles are going to shift in the next generation. It's going to change the allele frequency. Now that means that that population would be violating the Hardy-Weinberg equilibrium. It's not staying the same. And we would say that it's evolving. Now, so again, let's think about this example, and you guys can pause and talk about this. What if the brown frogs, let's reverse my supposition. What if the brown frog can't be seen by predators? And so let's say the brown frog can camouflage. Now, if that's the case, then the brown frogs are able to survive, and sadly, little froggies, let's say that a few of them are going to get caught by predators. Now, the brown frogs are surviving more, and think about that. That means that little recessive allele is going to be passed down to the generation next. So pause the video and think about, discuss as a class, what do you think the next slide is going to look like? Well, in the next generation of frogs, will we see more brown frogs or more green frogs? And we're back. And so what you should have come to a consensus is that there would be more brown frogs. And that indeed would be true. More of the brown frogs are surviving, and more of the brown frogs are then reproducing. And then we would see the population shift. Now, you can understand this can happen so often that you could be excused for saying, well, this is hardly evolution. But we'll talk about what ends up having to cause speciation. Right now, we're just looking at what happens to change a population and manipulate the frequencies. All right, so that is a good introduction to our Hardy-Weinberg. That would be our allele frequencies and natural selection.